So next, I would like to introduce my esteemed friend and colleague, Dr. Phil Erickson of the MIT Haystack Observatory. And you'll notice that all of the talks this morning have the same theme. This is doing Doppler shift or some sort of ionospheric sounding by receiving signals of opportunity from standard stations such as WWV. All right.
See, does this work? It's on, George. Yeah. I'm too loud anyways. Can I borrow that pointer?
There you go.
I've never seen a pointer that, well, this, okay, you're, for those of you who like dark things on dark backgrounds, it's going to be a little bit of a challenge.
Here, Phil, we also have green.
Oh, good.
Okay.
Green might work a little bit better in this case.
Thank you.
So, first of all, it's a pleasure to be here. I'm really looking forward to the next couple of days. And as Nathaniel said, you're going to hear a number of things having to do with this WWV station. And I will actually, I threw a slide or two in about what it is in case some of you have never really actually played around with it. Let's see. First of all, these are the co-authors. This is a collaborative project, okay? I'm just reporting a small facet of it. Other things are happening. I'm an assistant director at MIT Haystack Observatory, so I spend my career doing ionospheric and magnetospheric research. Everything I've done on this particular project has been done on nights and weekends, so this is, MIT did not pay for any of this analysis. Bill Lyles started all of it. Bill's responsible. It's all Bill's fault if you want to know why this is happening. Joe Duesenberry and Casey Kirby-Patel. Casey's a professor at UMass Boston. Joe is her student. They also helped with a separate set of analysis, which I won't report here, but actually already got reported in a talk at the 2019 ERSI meeting in January in Boulder. Ethan Miller, KAGU, who's back there in the corner, and Gary Bust, who is not back there in the corner, are at JHU, the Applied Physics Laboratory, and they were colleagues in this, and also Catherine Mitchell over at University of Bath in UK. I also have to acknowledge taxpayer support because of the National Institute of Standards and Technology, which is why that particular beacon is there in the first place, and Guido Rossum and the Python Collective for allowing me to actually do the analysis in some tractable amount of time. This is beyond my generation. Does anybody know who that is? John Cameron Swayze. He used to do ads for Timex. It takes a licking and keeps on ticking. So I put that in there just as a reference point, is that, you know, people have been worried about time sources for a very long time. NIST's bread and butter is to maintain frequency and time standards for the United States. So these are attractive signals. Lots of money is kept into keeping them accurate, and we don't have to do that. So much like the GPS cluster, where, you know, you're not spending $10 billion on the navigation chip in your phone, all the money's up in orbit. Here, there's a nice weighting in that a lot of the work is already being done by NIST, and inexpensive receivers can actually pick that off, and you're going to hear other talks having to do with different aspects of WWV. Now the question is, how do I move the slide? Right? Oh, right arrow. Look at that. All right, so as I said, it's all Bill's fault, and this is Bill's question. Can we look at the time ticks, not the carrier, but the actual 1-second ticks coming out of WWV? Is there any information on the ionosphere in there? Because you might think that that wave is going to go out of the transmitter, you're over here. It's going to bounce off the ionosphere, which is not a smooth, non-moving thing. It's got lots of irregularities. So can we do that? That might be an attractive thing to do for something like a space weather station, for example, but we have to think about a couple of things first. So, this is WWV itself. By the way, that's a QSL card from 1940, and you'll notice it's kilocycles, right? These are the transmitting towers for WWV in Fort Collins, Colorado. There's also WWVH from Hawaii, which covers the Pacific sector, and as Nathaniel's already mentioned, WWVB down at 60 kilohertz. As part of their time and frequency services, you can read this right off their webpage. This is a service to the community. This at one point was the way that people set lab equipment, of course, before the availability of GPS timing, global timings, that you'd use WWV to synchronize your clocks. And there's a reasonable amount of power coming out at HF, 2.5, 5, 10, 5, 15, 20, and 25 megahertz. 5, 10, and 15 are 10 kilowatts of power, pretty good. And they're synchronized to NIST time standards, which means that they're highly accurate. We ought to be able to take advantage of that. What does it sound like? Well, if you were like me, sitting in a bedroom in 7th grade playing with an SX-110, which drifted when you looked at it sideways. Nowadays, there are things like Kiwi SDR. I think we're even going to see a Kiwi SDR later in the conference on the web. And in fact, one of them is not that far from Fort Collins. This is one of the first signals I picked up, because it's really loud. Very familiar to hams, shortwave listeners, which is where I started at, and it sounds like this. World's most boring signal, right? And then you listen for a little while, and then the person says, ready? And then you set your watch, right? And you can tell when I did that. That was last night. Pulled off the web, by the way. Just hit the record button on the Kiwi SDR. Marvelous thing. Beats running a tape recorder off that. It turns out that NIST, because it's a time service, packs in a staggering amount of information into that signal. If you go around the clock from the top of the hour, there's all sorts of things happening in there. You alternate between different tones. There are announcements. That's part of doing space weather forecasting. We have buried in here, which is a challenge for people who are trying to use it as a measurement device, because there's so much diversity here, except for one part of it. And then that's what I'm going to be concentrating on. And by the way, there's also a telephone toll-free, not a toll-free number you will see here, which is what you used to have to do if you couldn't have your radio on, dial it up and set your watch by what you heard on the radio, the telephone. The 100 hertz subcarrier, which you can just about hear, which is that pulse, happens every single second without exception, and it's actually a binary coded decimal format, and there are things that pick that off. So for example, in there is buried the time of year, the offset from universal time, if they put a leap second in for this year, because NIST is a time service. These are all bauds that have a minimum length of 0.17 seconds. Some of them are longer because there's zeros and ones, but they go on and on. And so that's the one thing that's constant, as opposed to the other diversity that's happening. So I tried to simulate it just because I needed an analysis chain, and you got to start with something you know. So here's a simulated signal where I've already mixed the 10 megahertz WWV down to 0 frequency. This is frequency in hertz from the center. This is time, okay, at a sampling rate of 32 kilohertz. The carrier at 0 hertz, David is going to talk about next about watching that vary. Here it doesn't because it's a simulation. There's the 100 hertz ticks, okay? And it's an AM, so they're double sideband, all righty? I put a 20 dB fade every 6 seconds. There's a reason why I did that. Those of you who have listened to any shortwave signal, you realize that it often goes through deep fades. That's the real world. That's out of my backyard. So what do we got here? Well, QRM, that was interesting. Probably somebody's LED light. And, well, the receiver wasn't quite offset. I had a little bit of a frequency shift. There's the fading. There's some upper harmonics. What are those coming from? Are they coming from the transmitter? We'll find out. So that's just a fan dipole, and a fancy word for saying I threw some wire out my window. And this is the algorithm I came up with, thanks to the power of Python, and a package called Digital RF, which we at MIT Haystack have developed and have open sourced for the community. That is a open source container for voltage that is time coherent and is a marvelous thing if you're trying to do things where you're picking off random stuff here and there. SDR, I'm not even going to tell you which SDR I've used. Many can be used. So you record your complex voltages, and this is the chain that I came up with. You want to take this particular ticking, and you want to move it from here to there. So what do? You mix it down 100 hertz, and then you run it through a low-pass filter of 10 hertz. So now we've isolated that particular ticking. You then need to run it through a simple threshold detector. Where's the power above a certain level? And there's lots of tweaking in that. And then you want to run a matched filter. And anybody who's taken signal processing courses, matched filter says if you know what you're looking for, it's easier to find. You want to look for a pulse that's a minimum of a 0.17 seconds, because happily the NIST people have set that. And then you can run that through a filter, and it gets rid of a lot of the other stuff that is not the time ticking. So then you record the edge location. The refinement is that we then go back to the recording, and we use a different filter. We actually keep all of this. We knock out the carrier. We just have a little band pass centered at 100 hertz. We also locate the first few times that 100 hertz crosses 0. That way, if there's any amplitude turn-on variations in their transmitter, we might be a little less sensitive to that. And you throw it all into a wonderful HDF5 file. I can't say enough about HDF5. It's self-documenting. It's designed to be here for the long haul. And then you can do some analysis. This could be a student project, okay? This is just me playing around with some Python, again, with a cup of tea late at night. Here's a little bit of snapshots of where this goes. So here, for example, is after I've moved this thing from 100 hertz down to 0, and I run it through the low-pass filter. Wow, there's a pretty strong 1-0 signal there, okay? So I then run a matched filter, and anytime you see this triangle, the peak of the triangle is, I've matched something that is the length of the pulse I want to see. You'll notice, by the way, that here, the thresholding has a problem because there's a dip in the match filter, and I actually missed some pulses in here when I faded, requiring more tweaking. I also needed a coincidence detector to reject spurious matched filter hits that happened to be due to QRM that had the right length. So you do a little bit of jiggling, but that's not too bad. So this is the internals of that plumbing. Here's an example of one of the pulse detects. Okay, so here we are at 1.40 seconds. The kind of cyan is the original wave, and there's the 100 hertz pulse turning on. The blue is me after I've taken this and basically just notched that out, and there you can see the 100 hertz wave. So I record where the black is, which is this envelope turning on, and then I also record these green lines, which is every time I see the zero crossing happen after that, and I just save them. That's it. So once every second, I get a few measurements. And then I just looked at the statistics. And I was very puzzled because I shouldn't be getting any spread. These are perfect ticks. I should never see anything else. So what's going on here? And then I plotted the time I saw from second to second as a function of dB. Well, that shouldn't be spreading out either. So I went back and scratched my head a little bit, and this is for students in the room. This is what you do when you play with things. What you discover is the finding that when you have a fading, watch the detection with respect to the cyan. Did you see it wiggle there? When the thing fades down, the threshold detection does a little bit wrong. Watch, here we go. It's fading, fading, fading. Oop, there it goes a little bit. But if you watch carefully, the 100 hertz zero crossings do not move. They're actually locked. So there's two slightly different measurements in here. I knew that because I simulated it. So, boy, that's a lot better. Everything is happening precisely on 1 second because that's what I fed in. So now at least I know my chain is working okay. So now we want to get a copy of the transmitter signal, and that's where Ethan and Gary come in. It's called a Lyle's errand. Bill tells you to go collect something, and you go drive out in the middle of nowhere and do that. See Bill, he has lots more ideas like this. So this is near Fort Collins. There's the transmitter site, and there's the collection point. These guys drove out during the middle of the ERC meeting when I'm sure they were supposed to be hearing a very interesting talk. Instead, they were driving around in their car. Collecting some data close enough to the transmitter that, in fact, it's basically a copy of just something that's going by ground wave. Remember, this is 10 kilowatts, and that's 4,000 feet, so they're about, 1-point-something kilometers away, and perhaps a little strong. This is their gear. This is an Edison N210 software-defined radio, which has been around since 2004. That design is very, very stable. You see it used in a lot of research stuff. There's an advanced receiver research preamp there. It's about 20-something dB. That's just to condition the front end. Laptop recording using Linux, of course, and power conditioning, as I call it. Let's run it off the 12-volt. Apparently, nobody uses the word cigarette lighter anymore, but that's what it was. And so let's get in there. Let's go record. So you saw my simulation. What does it look like in real life? It's pretty good. That's the clean signal. And by the way, that's just a 30 dB scale. There are harmonics at 200, 300, 400, 500. They go on and on. They're just cut off by the plotting scale here. That's pretty clean. And notice I'm even using a different sampling rate, but it doesn't matter. They're there. So I should be able to detect that. That's what they look like. I'm just showing you not the zero crossings, but just the envelope detections, again, to save time. So that scale is about a millisecond, and the period of the wave is 10 milliseconds, 100 hertz. So I'm resolving things to less than a tenth of the period of the wave at the transmitter. So that's what's, even on the ground wave, there's a little bit of variation, but it's pretty clean coming out. Remember my backyard. So it's not data taken at the same time. Again, I wish I had more coffee, but I didn't, so I didn't have a chance to analyze all the data we have. But let's just compare the local signal we saw from a statistical point of view to the one I recorded in my backyard at Massachusetts. Yes, it's a different time. There you go. That's the ionosphere, folks. Look at, those are exactly the same scales. The ionosphere is spreading this by about 2 milliseconds, and it's very Gaussian. So the ionosphere is having some kind of impact, and now we just need to figure out what it means. But that's, the research community will be able to get their hands into this. This is a very inexpensive measurement to make. So that was my goal, to see if I was crazy, and this was all systematics, and me being a not such a clever person and somehow screwing up an analysis. I don't think I have. So in summary, there's John Cameron Swayze telling you that this has a lot of potential as a fairly simple ionospheric remote sensor, and you could distribute it. It's a very interesting signal detection problem for a student because you get to learn about signal processing and you get to break it and fix it again and rewind the data. What does it mean? That's why we do science. Much more work needed, and I want to point out that this is a collective effort. This isn't just me. This is just where we are right now. So I'll stop there, and I know we're going to have more about WWV, and I'm happy to take questions. Thanks. I just took that off. Anybody? Go ahead, Bob. Yeah. Right. No reason you couldn't. To me, it's an analogous to, if anybody knows, there are beacons, right, that people put out. Some beacons are modulated and some are not. WWV is a classic example of a modulated beacon, right? A CW beacon is the simplest thing because you don't have to remove any of the information if you want to track Doppler, right? But if you know what the information is and you can do some simple filtering, even, it doesn't matter what the signal is. WWVB has a time signal on it the same way. Track carriers from AM radio stations. The Dartmouth group has been doing quite a bit of that. And on the one hand, you can track things, variations very carefully, and my joke is the other hand, you embarrass a lot of radio engineers who watch their carrier go like this by about 5 hertz, including very large stations who should know better. But there's plenty of that information buried in there, and again, it's attractive because most of the effort is on the transmitting end. And at different modality, different propagation path, different refraction, really heavily refracted. Yeah, absolutely. Looking forward to it. Volodya. Yes, right there.
What would happen if you put on the ionosphere altitude the perfect conductor,
right?
Just a plane? Signal would not be spreading?
That's my conjecture, at least. I still have to prove that by simulating it. But
well, putting there, of course, conductor.
Yeah. But
my
I would
question
think.
is actually towards this 2 millisecond spread. Does it mean that reflection happens statistically in few different levels of ionization? If it's true, then you actually can monitor this micro scale changes.
Right.
Yeah. So
I'm hoping that that's where this leads. As Larissa, who's sitting next to you, studies, we know that the frontier of the research community is understanding ionospheric variability, right? And we know that there is a couple of percent ionospheric variability in, for example, electron density any day of the year if you actually look. Maybe we're starting to get a little bit of glimpse into that, but I need to prove that we're most sensitive to that variation and not, for example, to other kinds of refractive shifts. I really hope it works out that way. I think it would be fabulous. I have to also do the sanity checks on that spread to see, okay, does that make some physical sense in terms of what we know from other measurements? But yes.
Do it like in the morning, at night.
Yep, exactly.
Yeah,
In fact, my next step here, my next step is to take my wire out the window and basically just implement this, and every few minutes have the thing just start and record as a prototype, and then we'll see where that goes. That will go back to the Space Weather Station, I think. Just let's see if we can float this as a trial balloon for something that is lightweight, but that we could continue to do as a community. I'm really excited about that possibility, and again, it's all Bill Lyle's fault.
Thank you very much.
Thank you very much.